our last topic for Chapter 10 is looking at paired data. In this situation, we are still looking at means, not proportions. So, let's look at this situation. A researcher studied a random sample of identical twins who had been separated and adopted at birth. In each case, one twin, twin A, was adopted by a high-income family and the other twin, twin B, by a low-income family. Both twins were given an IQ test as adults. Here's the data. So, twins raised in high-income households had a higher mean IQ, 109.5, versus the other twins who were raised in low-income families, 103.667. There is a similar amount of variability in IQ scores for both of these groups. For twin A, the standard deviation was 9.47. For twin B, the standard deviation was 8.66. But with so much overlap between the groups, the difference in means does not seem statistically significant. So if we ran a standard two-sample t-test, like we learned in the previous video, it would probably not be a statistically significant difference. But that ignores the fact that this is paired data. Paired data result from recording two values of the same quantitative variable for each individual or for each pair of similar individuals. So, if we look at pair 1, both twin A and twin B had high IQ scores compared to the rest of the pairs. So maybe, genetically, they are just smarter than kids from other families. But the twin who was raised in a high-income family still had a higher IQ than the twin raised in a low-income family. So what we want to try to figure out is that difference the result of nurture? So we're trying to get rid of nature as a confounding variable when we are looking at the nurture aspect of family's income on a child's IQ. So instead, we want to look at the difference. So in this case, we're going to do twin A's score minus twin B's score. And you can see that in all but one pair, twin A had a higher IQ. If we graph the differences on this dot plot, we've got that there. The mean difference, and we're going to denote this as x bar sub diff, or you might see x bar sub d, is 5.833 points. So on average, twin A had almost 6 IQ points higher than twin B. The standard deviation of the difference is 3.93 points. Remember, these calculations are coming from this last row. Now, the method that you choose, whether you are doing a two-sample t-test or a paired t-test, depends on how the data are produced. To analyze paired data, start by computing the difference for each pair. Then make a graph of the differences, and you are going to use the mean difference and the standard deviation of the difference as your summary statistics. So, let's look at an example. So, does music help or hinder performance in math? student researchers Abigail, Carolyn, and Leah designed an experiment using 30 student volunteers to find out. Each subject completed a 50-question single-digit arithmetic test with and without music playing. For each subject, the order of the music and no music treatments were randomly assigned, and the time to complete the test in seconds was recorded for each treatment. Here's the data along with the difference in time for each subject. So, they have 30 student volunteers. They took 2 different math tests, one with music, one without music, and they recorded how long it took them to do that, and then calculated the difference. And they did music minus without music. So, we want to first make a dot plot of the difference in time for each subject to complete the test. So, looking at that last row, you make a dot plot. Okay? You guys know how to make dot plots. Part B says, describe what the graph reveals about whether music helps or hinders the math performance. Okay, so if we look here, and you want to describe this graph, talk about how music affects math performance. Well, there's some evidence that music hinders your performance on the math test because slightly more than half, 17 of the 30 subjects, took longer to complete the test when listening to music. Lastly, we want to calculate the mean difference and the standard deviation of the differences. So, if you take that third row, the difference row, calculate the mean and standard deviation using your calculator, you get the mean is 2.8 seconds, the standard deviation is 7.49 seconds. It says interpret the mean difference. So the interpretation is the time it took these 30 students to complete the arithmetic quiz with music was 2.8 seconds longer on average than the time it took without music. I'm going to flip to the calculator real quick. Remember, if you're trying to find the mean and standard deviation of a set of numbers, you go to Stat, Edit, type in your data. Now I'm going to go ahead and clear out the data that I have in here. Then you go to Stat, Calc, 1var Stats. Select the list where you typed your data, hit Calculate, and it'll give you S bar or X bar and S sub X, your mean and standard deviation. So, there are 2 ways that a statistical study involving a single quantitative variable can yield paired data. One is researchers can record 2 values of the variable for each individual. So, the example where we looked at investigating whether music helps or hinders. Or if you have a pre-test and a post-test to see how much you learned. Anytime there's a pre-test or post-test, it's going to be paired data. So a drug trial, if it's a diet pill, how much you weigh before and how much you weigh after, that would be paired data. The second situation is where the researcher forms pairs of similar individuals and records the value of the variable once for each individual, like with the twins' IQ scores. The twins are paired together, and you're comparing twin A's IQ and twin B's IQ. This situation could also happen if you create pairs. For example, if a cross-country coach wants to see if a certain workout plan makes the runners run faster. They could rank all of the runners, fastest to slowest. Let's say we're just looking at boys cross country, and then pair them up. So maybe the fastest two runners are paired up. One gets assigned to the treatment group, the other gets assigned to the control group. Then runners 3 and 4 are paired up. One gets assigned to the treatment, one gets assigned to the control group, etc. And you compare and see how their running speeds changed based on whatever workout program or diet or whatever. It is also possible to carry out a matched pairs experiment using method 2 if the researcher forms pairs of similar subjects and randomly assigns each to treatment assigns each treatment to exactly one member of the pair, which is what I just described. So first we're going to look at confidence intervals. If you're constructing a confidence interval for a mean difference, you got our 3 normal conditions. Random. The paired data has to come from a random sample of the population or from a randomized experiment. You've got the 10% condition, where the sample size has to be less than 10% of the population. And then you have the normal or large sample. So either the population distribution of differences is normal, or the number of differences, or the number of pairs, is greater than or equal to 30. If the population distribution of differences has an unknown shape and the number of differences in the sample is less than 30, you need to create a graph. Make sure there is no strong skewness or outliers, which is what we did in the twin study. We had a dot plot of the differences. So, if you are going to do a one sample t interval for a mean difference, or paired t interval for a mean difference, as long as your conditions are met, a C% confidence interval for the mean difference is given by this formula. This is the same as the formula we used for a one sample t-test. We have our generic, or one sample t-interval. We have our generic confidence interval formula, where you have the statistic plus or minus the critical value times the standard error of the statistic. In this case, instead of just having x bar, we have x bar sub d, or the mean of the differences. Instead of having the standard error be the standard deviation over the square root of n, we have the standard deviation of the difference over the square root of the number of differences, or the number of pairs. T star is the critical value, with C% of the area between negative T star and positive T star for a T distribution with n-1 degrees of freedom. Remember that for paired T intervals, n is the number of pairs. So let's look at this twin example again. The data from the random sample of identical twins are shown again in the following table. Construct and interpret a 95% confidence interval for the true mean difference in IQ scores among twins raised in high-income and low-income households. So we're going to go through state, plan, do, conclude. State. We have a 95% confidence interval for the mean difference, where the mean difference is the true mean difference, high income minus low income, in IQ scores for pairs of identical twins raised in separate households. Plan. We're doing a one sample T interval for the mean difference. Check our conditions. We have a random sample. We know that the 12 pairs were randomly selected. 10% condition. It's pretty safe to assume that 12 is less than 10% of all pairs of identical twins raised in separate households. And then the normal or large sample. We do not have a large sample, we only have 10. We don't know that it's normally distributed, so we make our dot plot of the differences. There's no strong skew or outliers. For do, if you're doing it by hand, you need the mean and standard deviation of the differences. Since there are 12 pairs, n is 12. Our degrees of freedom is n minus 1, so 11. You can find t star by doing inverse t. Plug everything in the formula and get your confidence interval. Or you can use the calculator. If you're using the calculator, when you go to the list, type in the differences. Once you have your differences typed in, you can go to Stat, Test, T-Test, say we want Once you have your differences typed in, you can go to Stat, Test, T interval, which is 8, select Data, because we're going to use our data in L1, and our confidence level is 0.95. And it spits out the same interval, or nearly the same interval with rounding differences that we had on the slide. Now, conclude. We are 95% confident that the interval from 3.36 to 8.330 captures the true mean difference of high minus low in IQ scores among pairs of identical twins raised in separate households. Now, let's take a look at significance tests. Your null hypothesis is going to be the mean difference equals some number. The most common is that the difference is equal to 0. The conditions for the hypothesis test are the same as they were for the confidence interval. We need random data, 10% condition, a normal or large sample. So, if you are doing a paired t-test, also called a one-sample t-test for a mean difference, once you know the conditions are met, if you are going to test the hypothesis, the mean difference is equal to 0, you compute your test statistic, which is t, the same way that you computed your test statistic for a one-sample t-test. The mean difference minus 0 over the standard error, which is the standard deviation of the difference divided by the number of pairs, square root of the number of pairs. You find the p-value, just like we do for other hypothesis tests, by calculating the probability of getting a t-statistic this large or larger in the direction specified by the alternative hypothesis, using a t-distribution with n minus 1 degrees of freedom. So, researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas or sodas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which subjects took caffeine and placebo was randomized. At the end of the 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. The table displays data on the subject's depression test scores. Higher scores show more symptoms of depression. So, question is, do the data provide convincing evidence at the alpha equals 0.05 significance level that caffeine withdrawal increases depression score on average for subjects like the ones in the experiment? So, we're going to do our state, plan, do, conclude. State. Our null hypothesis is that the mean difference is 0. Our alternative hypothesis is that the mean difference is greater than 0. And we are defining the mean difference as the true mean difference, placebo minus caffeine, in depression score for subjects like these. We're going to go ahead and use alpha equals 0.05 because it was not specified in the previous slide where it described the situation what level we were using. Plan. We're doing a paired t-test for the mean difference. Checking our conditions. The researchers randomly assigned the treatments, and we're looking at the order of the treatments. Placebo, then caffeine, or caffeine, then placebo to the subjects. Because it's an experiment, we do not have to check the 10% condition. Our sample size is small. It's only 11. So we need to check either a dot plot, histogram, box plot, something. We have a histogram here. It's not strongly skewed and there are no outliers, so we're good to proceed. Now we need to go ahead and calculate our t statistic and our p-value. So you will notice that in this data set, the difference is not given. You can go ahead and calculate that on your own if you want to. We did specify earlier that we're doing placebo minus caffeine. Or you can have the calculator do stuff for you. So I'm going to switch back to the calculator. Since we said we are doing placebo minus caffeine, I am going to enter placebo in L1 and caffeine in L2. Once you have the data entered, go over to L3. If I go up to the top, I'm going to say I want L3 to be L1 minus L2. So my L1 was the placebo, L2 is the caffeine, so I'm doing placebo minus caffeine. When I hit enter, it calculates the differences for me. Now I'm going to do a t-test on L3. So if I go to stat, test, t-test, I'm using the data. My null hypothesis was that the mean equals 0. The data I want to use is L3. That's the difference. And my alternative hypothesis was greater than. So I'm going to leave that and go to calculate. Now, this gives me my t statistic and my p-value. Let's see how this compares to what's on the slide, doing it using the formulas. If we're doing this by hand, you would calculate the differences by doing placebo minus caffeine, find the mean of all of those differences, the standard deviation of all of those differences, calculate your t statistic, which would be x bar minus 0 over standard deviation of the difference divided by square root of n, to give you a t statistic of 3.53. 3.53. That's what I got there. Then you can use n minus 1 degrees of freedom, so 10 degrees of freedom, and figure out the p-value either using the table or TCDF. Using TCDF, you get 0.0027, which is what we got as our p-value using the t-test function. For the conclusion, based on the p-value of 0.0027 being less than alpha of 0.05, we reject the null hypothesis. We have convincing evidence that caffeine withdrawal increases depression test score on average for subjects like the one in the experiment. So, the hardest part is determining which procedure to use. A two-sample t-test, like we looked at in section 10.2, requires that data come from independent random samples, from the two populations of interest or from two groups in a randomized experiment. The paired t-test requires paired data that come from a random sample of the population or from a randomized experiment. Ultimately, it depends on whether the data is paired or not. You have to pay attention to how the data were produced. So let's look at some scenarios. All we want to do for these scenarios is determine whether we're using a two-sample t-test or a paired t-test. Before exiting the water, scuba divers remove their fins. A maker of scuba equipment advertises a new style of fin that is supposed to be faster to remove. A consumer advocacy group suspects that the time to remove the new fins may be no different than the time required to remove the old fins, on average. 20 experienced scuba divers are recruited to test the new fins. Each diver flips a coin to determine if they wear the new fin on the left foot and the old fin on the right foot, or vice versa. The time to remove each type of fin is recorded for every diver. This is going to be a paired t-test. You have two measurements of the same variable for each diver. Every diver has one new fin, one old fin, and they're comparing how long it takes them to take off both of them. So it is a paired t-test. Next situation. To study the health of aquatic life, scientists gathered a random sample of 60 white piranha fish from a tributary of the Amazon River during 1 year. The average length of these fish was compared to a random sample of 82 white piranha from the same tributary a decade ago. This is going to be a two-sample t-test. The data come from independent random samples of white piranha in 2 different years. There is nothing that pairs the piranhas in the 2 different years. Next scenario. Can a wetsuit deter shark attacks? A researcher has designed a new wetsuit with color variations that are suspected to deter shark attacks. To test this idea, she fills 2 identical drums with bait, covers one in the standard black neoprene wetsuit and the other in the new suit. Over a period of 1 week, she selects 16 2-hour time periods and randomly assigns 8 of them to the drum in the black wetsuit, The other 8 are assigned to the drum with the new suit. During each time, the appropriate drum is submerged in waters that sharks frequent, and the number of times a shark bites the drum is recorded. This is going to be a 2-sample t-test. The data come from 2 groups in a randomized experiment, with each group consisting of 8 time periods in which a drum with a specific wetsuit, standard or new, was randomly assigned to be submerged. And that is it for Chapter 10.